Let's now work on variation of parameters method. So as you can remember from the last lecture, we were using the method of undetermined coefficients to solve non-homogeneous ordinary differential equations. However, undetermined coefficients isn't always the best way to solve these differential equations because sometimes our non-homogeneous part of the differential equation, h of x, could be a function like tangent, logarithm, or other functions that we would not be able to use undetermined coefficients. In this case, variation of parameters emerges, and it's a very accurate method. Unlike undetermined coefficients, where we would guess our particular solution, we don't have to do that anymore. We would just find our particular solution. It is a little bit tedious, but it is going to give us accurate results. Undetermined coefficients, on the other hand, is also a very useful method. So sometimes problems might ask you to use specifically variation of parameters or undetermined coefficients. So it is a good idea to master both of these concepts. So now let's work on what a non-homogeneous ordinary differential equation means. Non-homogeneous ordinary differential equation means that on the right-hand side we have a non-homogeneity, which means it's a non-zero, either a number, a function, or any kind of non-zero factor we have on the right hand side. However, on the left hand side, we would have a normal second order differential equation, and it is important for us to put this in standard form. We would have 1 for the coefficient of y double prime, and we would have functions of p of x and q of x in front of y prime and just y. So just like in method of undetermined coefficients, our solutions will be y general will be yh plus yp, which means yh is for y homogeneous and y particular is yp. So what was y homogeneous? Well, basically on the right hand side you're just gonna set this h of x equal to 0 and solve for this differential equation and get your homogeneous solution, YH, and on the right hand side we're going to get the particular solution. And for the particular solution, the method on undetermined coefficients would create guesses, and as long as it doesn't create linear dependence with the homogeneous solution, we would get that Y particular, and we would basically add these up and get our solution. However, unlike undetermined coefficients, we now use some formulas to get these solutions. So these formulas are really derived from the method of variation of parameters, and they're pretty similar to reduction of order. However, I think it's unnecessary to use all of that method to get those. Instead, we could just use these really easy formulas to use variation of parameters. So our particular solution will be u1 y1 plus u2 y2, where u1 and y1 u2 are basically different functions, and we have this integral function to find what u1, which is the negative integral of y2 times homogeneous part of the differential equation h of x divided by the wrong skin of y1 and y2, and taking that integral will give us u1. Likewise, we will have the u2 integral. U2 is going to be equal to y1 integral of y1 h of x divided by wrong skin of y1 y2 dx. So, just like we did in method of undetermined coefficients, it's really useful to get our y fundamental. Our y fundamental will help us get y1 comma y2, and these y1 and y2 are essentially what we need to build u1 and u2, and once we have those, our particular solution becomes really easy to find, and our particular solution plus the homogeneous solution gives us the general solution. So once we find this, we want to also find the wrong skin, because the wrong skin of y1 comma y2 will help us get these u1 and u2. So we will be using wrong skin a lot in this method of variation of parameters. Now let's solve this example problem. So, as you can notice, we have a non-homogeneous ordinary differential equation, and we could solve this differential equation using method of undetermined coefficients because we are able to get a nice guess for this 5e to the t part of the differential equation, and we would be able to solve it completely fine. But I want you to stop this video and try to solve this using variation of parameters. Now, if we use variation of parameters to solve this problem, let's start with finding the homogeneous solution. R squared plus 4r plus 4 equals to 0. So we will have r plus 2 squared equals to 0. And this will mean our roots will be -2. And these are equal real roots. So our y homogeneous will be c1 e to the minus 2t plus c2t e to the minus 2t. Okay, our fundamental set of solutions will be e to the minus 2t comma t e to the minus 2t. Okay, and let's find the Wronskian since we're going to use that a lot. So our Wronskian will be if we put the first solution and the second solution here, and the respective derivatives just like this, e to the minus 2t minus 2t e to the minus 2t. Okay, and we're gonna multiply these ones and subtract these ones. So we will have e to the minus 4t minus 2t e to the minus 4t plus 2t e to the minus 4t. And we will be canceling this, so our Wronskian ends up being e to the minus 4t. Okay, now that we have our Wronskian, we can go ahead and use variation of parameters to solve this differential equation. So our particular solution will be u1 y1 plus u2 y2. So let's start by finding u1. u1 is the negative integral of y2. y2 is t to the minus 2t multiplied with the non-homogeneous part of the differential equation, 5e to the t, divided by the Wronskian, e to the minus 4t dt. If we go ahead and solve this integral, if I want to simplify this first, so we will have -5 integral of this -4t can come up as e to the 4t to the top, so we will have t e to the 3t dt. And we can use integration by parts to solve this. I will use the DI method, and this will give us, you can use the UV method as well. All of these methods works completely fine. So we will have t e to the 3t over 3 minus e to the 3t over 9, and these are going to be multiplied with -5 here. Okay, now that I have my u1, now I can go ahead and solve u2. u2 will be the integral of y1 e to the minus 2t multiplied with the non-homogeneous part 5e to the t, 5e to the t, divided by the Wronskian e to the minus 4t dt. And this will mean our integral is u2 equals to 5 integral of e to the 3t dt. And basically u2 will be 5 over 3 e to the 3t, and that's it. So if we want to solve for the y prime, basically what we need to do is gather u1 and u2 and multiply those respectively with y1 and y2. So this guy multiplied with y1 will be, I want to first distribute this -5 inside, so u1 is going to be -5 over 3t e to the 3t plus 5 over 9 e to the 3t. And u2 will be, since we found it already, 5 over 3 e to the 3t. And from the fundamental set of solutions, y1 was e to the minus 2t, and y2 was t e to the minus 2t. All right? Yeah, just like that. So we're going to multiply these guys out. So the y particular will be -5 over 3t e to the 3 plus 5 over 9 e to the t, and plus 5 over 3t over t e to the t. And these guys cancel out. So y particular will be 5 over 9 e to the t right here. So our general solution will be y homogeneous plus y particular equals to y general, and our y homogeneous was c1 e to the minus 2t plus c2t e to the minus 2t, and y particular will be 5 over 9 e to the t, and this will be equal to y general.